Welcome to the Bytecode. I'm your host Shafu, and today's episode is with Nick, who's going to walk us through the fuel specs. Nick, thanks for taking the time.
Awesome. Yeah, thanks for having me.
Y-
Yeah, let's dive into it.
For sure, for sure. Yeah. So maybe if you could give a brief introduction to fuel for those that don't know what fuel is, that would be great.
Yeah, for sure. So we like to call Fuel an operating system for rollups, and basically, simple way to put it is we're launching our first rollup with this new design onto Ethereum. That'll be the Fuel Ignition rollup, and that'll hopefully go live later this year. And we were actually the first optimistic rollup to deploy to Ethereum. So we deployed the very first and unfortunately only actual rollup to Ethereum, which has become kind of a meme onto itself. And I guess are one of the only teams that decided not to reproduce the EVM 500 million times. We chose a different path of really trying to fix a lot of the problems we saw as builders, right? In working with Ethereum, working with blockchain, and try to build a different kind of architecture that basically and hopefully solves a lot of these really key kinds of issues that everyone runs into with blockchain development, but also can be an expansive framework for everyone to build their own rollups, their own sovereignty as a blockchain dev. But for now, I think to keep the focus and to keep it simple, um, you know, we'll go live with our kind of V2 rollup later this year, and it'll be an optimistic rollup. And yeah, the core components of that will be the Fuel virtual machine, and then we have our own tools, SDKs, and language. The language being Sway. Yeah.
Nice. Nick, I have to ask, please define a real layer two.
Hmm. So the way that I frame it is like I think layer twos and layer threes are like a very broad spectrum of category of thing. And I think that's really just describing the layers of the system. So layer zero considered to be like the social layer. That would be like, social slashing, etc., social forking. Then you have like the layer one, which is effectively like Ethereum. And then you would have things that are built on top of or around these layer ones. And those would be layer twos. And then even for fuel, layer threes built on top of those. And so the way that I would define it is it's really a blockchain that is going to use another blockchain for a key component of its system. So whether that's settlement or security or security also being a component of like data, or some other major property of the chain is going to basically use a layer one for those properties. So for fuel, we use Ethereum for security, for decentralization, for things like forced transaction inclusion and DA, and as well just inheriting sort of the vast decentralized security that Ethereum offers because it has the kinds of properties we're looking for. So um, so I would just describe layer twos and layer threes as like a broad topic, and then I would describe a roll up as being a layer two or a layer three that actually inherits the security of Ethereum. So that's the way I define it, and that really means that all of the data is published through Ethereum on DA, whether it's through call data or 4844. There's full fraud proofs. There is basically everything you're looking for in terms of really inheriting the security of the underlying chain. And so that would be the way that I would describe a roll up versus like a layer two. So roll ups are like far more poignantly secured by the layer one, whereas layer twos could be like, a Validium or where it's got DA somewhere else, it's got, different properties somewhere else, and layer threes similarly. Like I think it's like a broader thing. And as well, you could have like, a layer two that does its state transitions through a ZK, but it posts the state transition data on a DA layer. So like you can have different variations of that. So that's sort of the way my mental model works around it. That's the way I perceive it. And I know the community still hasn't fully decided this, but I think that like, there's a lot of like roll-ups that are not really roll-ups. They're publishing DA somewhere else. Okay, then immediately you're not inheriting the security of Ethereum. So you're already something else. You're not a side chain. You're maybe better than a side chain, but you're not a pure rollup. So for us, for our ignition rollup, that'll be a pure optimistic rollup on Ethereum. Yeah.
Okay, so yeah, I think anyone who's watching this is like has a broad understanding what a layer two is. My question was about when you said in the introduction, unfortunately, we are still the only real layer two.
The only
What do
real.
you mean? Yeah, okay,
Yeah,
re-roll
yeah.
up. What do you mean by that?
I mean that unfortunately, Fuel V1, which is kind of ironic, was the only rollup that actually published all the fraud proofs, has no multisig, publishes DA to Ethereum, and did the whole thing.
Okay.
So, and had forced transaction inclusion. So, like basically, Fuel V1 is, a good example, I think, of where every rollup wants to be, right? It's where Optimism and Arbitrum want to go to, and they're on that pathway to doing it. But I think that for me, no one's actually still done it yet, and like Layer 2 beat and other things show that basically. Yeah.
Yeah, that's true. So you guys actually have a functioning fraud-proof system and all that already in production?
Caveat. So that was for Fuel V1, which we launched in December 2020.
Okay.
The current architecture we're launching, that will launch with like maybe 3 pies, ideally met on the security spectrum. So we're still working out our fraud proving and still working out how we would do multisigs and upgrades. But basically, there's some really nice solutions. So for us, we do a technique called hybrid proving, and that is basically using an optimistic rollup design. But instead of doing this complex IVG, we just use like SP1 or RISC-0, and you just feed in the invalid state transition into a ZK proof and then prove it to Ethereum. So no complex games or like back and forth, like it's a
Mm.
single round game. So we're still working through that, and fortunately, some of the architecture has gotten a lot better. Like when we started using RISC-0 and SP1, it was like a nightmare, and so like things have progressed. But for Fuel, like we like to consider ourselves like ZK pragmatists. Like we like
Mm.
ZK a lot. We want to use it across our design. We think our design like works really well with ZK, but we use it like where we think it can be used because like the Fuel like unoptimized the Fuel client right now can do like 12,000 TPS per core. So you're not going to run that through a ZK. It's
Yeah.
like it doesn't make a lot of sense. So but if you have like 20 TPS, like maybe you could make the economics work to do a ZK right now, but it's still really expensive, right? So yeah.
Makes sense. Makes sense. Awesome. Should we start looking at the specs?
Yeah, let's do it. Cool. So this is our fuel specs, and by the way, like I think we're still in a phase of our project where we're getting our documentation still together. There's so much to document. We are going to be putting together like a really comprehensive fuel book that outlines a lot more of our architecture and our ideas and our philosophy. But right now, like we'll just focus on the specs, like for the purposes of this episode. But basically, yeah, the specs sort of outline some of the core critical ideas for what makes fuel like great and efficient. And I think to kind of dive into this a little bit, and this is available at like docs.fuel.network. And yeah, so to start this off, I think a core piece of what the specs outline is how the fuel virtual machine works. But it also outlines some other key things. So it outlines our transaction format, how to compute identifiers, the validity rules for transactions, and as well like what kind of cryptography we support, what kind of cryptography we use, as well our ABI specification, and as well the storage slot initialization, which is seemingly very, very useful to have, and then as well our block header design. So it includes like some really key critical information. What we'll be adding to the specs soon will be how our bridge works, so our canonical bridge to Ethereum, how some of our security works around like how we actually secure all the infrastructure. So things like that will be going into the specs and into the docs. But right now, this is more like the design, the literal design of how fuel works and how fuel state transitions. So that's sort of what the specs cover. So yeah, some high levels here, fuel VM, and then we do have our POA block building mode network specification here, which is just more or less describing in sort of the single block building mode, how or a single block builder mode, how we actually do that and perform that, and then as well just testing. So this will all get expanded as well, and with future subsequent updates. And we'll also go into how we're thinking about multiple block builders, so decentralizing block building with sequencing, and also how we think about cross-chain interoperation between builders, which is another thing that Fuel is very good at. So yeah, maybe just to go into the transaction format to start. So I think some high level things to know about the Fuel VM. So we come from like basically the EVM space. So for us, like I've unfortunately spent a large part of my life staring at the EVM. Not to say that I don't know if that was really worth it time wise, but I've unfortunately learned too much. And so the EVM is sort of where we come from, but when we were designing the Fuel VM, we also had the chance to look at, Move's architecture. We looked at Solana. We looked at a bunch of different architectures, Wasm, RISC-V, and basically what we felt was that a lot of these different architectures didn't cover the kinds of problems that I think we typically see in blockchains, and they had no solutions for a lot of things that we think are pretty existential when you're designing these sort of like global, virtual machine systems where like, the entire world's going to be running these on nodes. We're going to be processing everyone's transactions through it. So you better think carefully about your design choices. And unfortunately for Move, we felt it was far too stateful. So it tried to treat everything like state. And then with the Solana virtual machine, it really didn't answer a lot of our critical questions about how you actually cryptographically verify everything and how you get rich cryptographic verification of state transitions. So not really good for light clients. Like they're building one, but it's like a sampling based light client, which tells you everything you need to know. It's like, oh, we can give you some data here. Like this is probably something, and then similarly with Move, it masquerades as something that wants to be safe and secure, but I think it just overly uses state and state locks in order to do that. And that's not really inferring, in our opinion, a lot of safety. It's really just far too stateful. So the Fuel VM tries to recognize a few key things that we wanted to build a virtual machine that's very fast and performant, obviously. So like it kind of like building a RISC-V emulator, but at the same time, take into consideration all these things that we do with blockchains and like what the problems of blockchains really are. So that blockchains want to talk to each other. They want to interoperate. Even with ZK, you don't just want to prove that the state of things is true. You want to prove a specific thing that happened in a specific chain at a specific time is true, and like so you want to have rich light client verifiability to make blockchains communicate with each other really, really well. And so we designed our block design around interoperation of blockchains. We designed it around performance, and we designed it around state minimization. So state minimization is probably one of the key things that at a high level we try to tackle. And so a lot of the design might seem a little counterintuitive initially, but it's really to address some of these bigger issues. And we kind of say some of these issues are kind of like global warming. It's like, it's there, it's like around, like it doesn't really metastasize all the time, but like every now and then you get kind of like a warning, like, oh, maybe this isn't good. Like just look at like Solana's state size, just look at it one day, just take a look and then just be like, it's like a lot of terabytes of state there, and then like, and just think that's like, people haven't even started using it yet. It's like just shitcoiner. So where are we going from here? Like, what's the solution to that? How are you actually going to holistically address it, right? And then secondarily, interoperation is another one. Like, we know we want these chains to talk to each other now. People are going to build blockchains, but we haven't addressed like the sophistication of, or sorry, not the sophistication, but like the very complex design that the EVM has for doing blocks, which doesn't make interoperation very nice. And so basically, like, we're going to have to jump through a lot of hoops to make all these blockchains talk to each other. Whereas if the block header was just different, the way that the block was designed was just different, you could have better communication. It's just like some subtle changes would actually make a big difference. But due to backwards compatibility, you can't really do that. So yeah, the Fuel VM tries to kind of encompass all these different things into a single design. And then we also encompass some other ideas around just how metering and optimistic verification works so that you get a nice virtual machine that's very, very fast. It can be brought down to the lowest levels of like virtual machine construction. You can do just-in-time compiling and other things eventually. But as well, it like brings in all of these concepts and these ideas around how blockchains actually work into a machine design. And we really think that no one's actually done a good job of this. So basically, like, I think the core idea is that like I just don't think a lot of teams are thinking about this. I think it's kind of like copy pasta, cash grab out there, and so really like we wanted to take a different approach because I think these are really interesting design problems, and we have the answers to them, but you gotta do the work to combine them. So yeah, to come into some of our transaction format, just to start it off. So Fuel has a script transaction, a create transaction, and a mint transaction. Mint is really just for more or less how we're designing the chains now, but that doesn't necessarily need to be here for all designs. Create and script are maybe the things to focus on. So Fuel has scripts, and we have smart contracts, and we have as well things called predicates. So we have a virtual machine that is multi-context. So it can work in multiple different ways and in multiple different situations. And we can add more context too. So it's not just that these are the only contexts. Like we might discover there's some new way to state transition a blockchain. And so Fuel would be able to add that concept into its into its virtual machine design as well. So basically, we have a very flexible design in terms of how these different contexts work. So scripts are a big part of that. And then as well, create is for creating Ethereum style smart contracts. So when you're using the Fuel VM, you're not really leaving behind what you get with Ethereum. You still get all the same niceties of Ethereum style smart contracts and storage and everything else, but it's just designed in a way that encompasses a lot of other nice concepts that I think the EVM really missed. Another key feature is that Fuel transactions have inputs and outputs. So they actually have a native state access list. And this is based around a UTXO model. So we have different kinds of inputs, different kinds of outputs, different kinds of witnesses, and basically different kinds of transactions. So it's a lot of complexity, but it allows you at the transaction level to do a lot of the kinds of state transitioning and settlements that you want with a virtual machine, right? Like instead of going into code, making everything smart contracts to do certain things, like we can settle a lot of different things just with the way the transaction works itself. So certain inputs are things like coins and contracts, and then you have messages, and then certain outputs are coins and contracts. And then you have some additional outputs for things like change. And, we also factor in the design of like a really nice thing about Ethereum is that you can make a transaction and you don't know what the state's going to be. You like leave it up to the builder, right, to decide what the state's going to be. And that allows us to have things like Uniswap and like these other designs. And so we bring that concept over to UTXOs and we say like, you sign over the transaction, and you'll see later, when you sign over a smart contract transaction, the state hashes for it, which we notate in the transactions, are zeroed out. And so basically, you sign over the zeroed out version, and then when you actually make that transaction, the builder comes in and fills it in over data. And that allows other blockchains to introspect the block, right? And find those state hashes and those state changes. But it also allows the user to make normal transactions like Uniswap transactions. So like it's this little trick that we do, but we understand that builders are going to do a lot here. So Fuel expects the builder to fill in a lot of information. And right now we do this through our system of smart contracts, but we're also expanding these concepts to other things where, like even recently, we discovered a way to build Uniswap v2 without smart contracts, which is kind of a crazy thing to say, but we do it through using spending conditions and native assets only. And so these
Nick,
kinds of
is that similar to how Bitcoin script works, for example?
Yes, yes. So when
Okay.
we get into predicates, you'll see we took a lot of influence from Bitcoin's pay-to-script hash design. Even though Bitcoin's very limited, right, in terms of its machine and what it can do, the concepts of basically conditional asset-based state transitions this way is like super powerful. And we'll get into some of those concepts after. But I think you'll start to see like some of the superpower of the design because when you build things in a certain constrained way, it gives you so many more opportunities for parallelism and for atomically processing different pieces of transactions, which is sort of like if you want to ask yourself the question, like, let's just forget about optimistic rollups. Let's go right to ZK, right? Wouldn't you want to be able to take different pieces of the execution and send those off to provers and then have them come back? Like just little isolated pieces, right, of execution, right? You want to be able to like take chunks, right? And do that in a ZK and know that that chunk, once you've done it, it's not changing. And so we know that a lot of smart contract execution can be built this way. It's just most VMs don't have facility for it, but we provide that like across the board with predicates and those conditional scripts. So we'll get into that after.
Yeah, another question, Nick,
Yeah.
just quickly. For me personally, I always found UTXOs to be unintuitive, compared to the just transaction model.
Yeah.
Doesn't that make just programming in Sway or something, doesn't that make it more complicated?
So surprisingly, no.
Mm.
So for example, I can just open so Sway Dash Playground is our like in browser playground here. So I'll give you some examples here of what smart contracts look like for us, and you'll notice all of that complexity doesn't exist. It's
Mm.
this counter contract here looks pretty much the same, even though it's in Sway, as what you would get in Solidity. You have to realize that the underlying asset system is kind of tucked away. Similar to like when I'm building smart contracts with Ethereum, I'm not thinking about the transaction format itself. Like I'm not thinking about it.
Okay.
So you can think of the UTXO model as it's an underlying superpower that you have that you can tap into, you can design around, but you don't need to use it right away. So like even here, we have a full Solidity transpiler as well. So like I could select like the counter contract here in Solidity and just compile that over. And you'll notice that there's almost no difference between the contract design. And that's because the state system itself is very similar to Ethereum in the way that we conceive of state, right? And the smart contract paradigm that we have is very similar to Ethereum in the way that we conceive of smart contracts. So our kind of way to say like, hey, what if you could build things like Ethereum, but then you could supercharge them with like native level assets and UTXOs and full parallelism, all these additional ways that you can build things, all these additional ways you can like supercharge your app. So that's really the way that we think about it. But you can always do it the Ethereum way with Fuel if you want.
Okay.
You know,
Nice.
you can always take like here we have like a voting contract. You can always take a very stateful design like this, right? Port it over, and the storage and everything else is very similar. And the concepts of the user experience are similar. It's similar to Ethereum that way. So we don't forget about what we like about Ethereum, which is like some of these concepts. But what we want to do is push devs to go like, okay, this is the way you do it in Ethereum, but let's go the crazier way. Let's do it the Fuel way. And the Fuel way is like, could you do it with just assets and just state transitions, just settle what you need to settle? And basically, we have this concept of rehydration where you rehydrate the state, you let the builder rehydrate the state. And if you could do it that way, then you can achieve something even greater with these constructions. Like you can push the design of smart contracts further because now globally, you're just witnessing asset settlement. But different builders are going to have different pieces of state, and that's a whole new concept that we're using with Fuel due to state rehydration. So for us, like we want to push devs to do things in a more interesting way. Yeah.
Okay, a couple of questions here.
Yeah.
Uh, First one, how powerful is the transpiler?
So it's pretty powerful. It does 27 of the 31 compound contracts. So
Hmm.
like compound V3. So it's getting more powerful all the time. Um, but we think of it more like a learning tool. So like we don't want you to like lean on a transpiler. We want you to use it to like learn the language and then write things in a more interesting way. But we're coming up with some cool designs here. So like for example, Fuel has native assets in our virtual machine. And so basically, like you can build an ERC20 contract at the application level. But what you would really want to do is build it at the native level. And so, like right now, when I transpile this ERC20 contract, it's just giving me a stateful application level token. But due to the fact that tokens follow a standard, like the transpiler will get smarter and it will understand, hey, this looks like a token. Like, would you like to do it the native way in Fuel? And it'll basically give you some additional functionality there. And so, like on the right hand side here, I'll just turn off Solidity for a second. We give some examples here of what a real standardized native asset looks like, and you can see that what's really cool is there is no transfer functionality in the token. There is no like transfer from or approve. You just have minting and burning conditions, and the native asset system takes care of the asset itself. So like you mint the asset to the user, and then they have the asset. And then if they want to use that in a smart contract, they actually use a script and they push it through a call into the smart contract. And that's how you get the assets into different smart contracts. And so like you can basically build all kinds of new push and pull primitives with that, where you don't need to be bound by a proven transfer from user experience. So basically, like you can do a whole new paradigm here of how you want to manage and create assets, and you get to leverage that native asset system. So it's like, what if every token on Ethereum could have the same properties as ETH does on Ethereum, right? That's the same way to think about it. It's like ETH can be pushed through calls, and you can use it in more extraordinary ways, and it's a lot cheaper. Fuel brings that to a whole new level, or like, okay, well, every smart contract can emit native assets. They can create them, and then basically this transaction model can have multiple native assets, and it can push them and pull them through contracts, or just settle them through predicates and not even touch smart contracts at all, which is really the wild thing that you really want to tap into. Yeah.
Interesting. Yeah, Nick, you're getting a lot of notifications in the background. If you
Oh
could,
yeah, here, let me see if I can shut some of that off.
yeah, no worries, no worries.
My Telegram uh, all day.
Yeah, so okay, so the UTXO stuff, basically, to summarize, if you don't want to use it, it's abstracted away. If you want to do some really powerful Fuel native stuff, you can use that if you
Yep,
want to. Okay,
absolutely.
interesting.
Yep.
Okay, the other question would be, but you answered that. What are native assets? But anyone, it's permissionless. Anyone can emit native assets, which is
Yeah,
it's
every
really
smart contract can emit their own kinds of native assets, and they can emit unique assets like NFTs, or they can emit fungible assets. If you look at in our format here, this might be helpful to illustrate it. So here is the asset ID in the spec, which is just the contract ID and a sub identifier. So that's how you calculate the asset ID. So with this, you can basically build complex like NFTs, right? The sub identifier is the NFT hash from a smart contract, or you can have that as just like a number zero, right? It's like the base sub identifier, and so the smart contract just emits one, and a smart contract can emit any kind or any number of different colors of native asset. So basically, like you can have a smart contract that emits all forms of NFTs if you want. Like you can do things like that. And what's cool is like in like a Uniswap v2 context, right? you can have all the LP tokens emitted from the same contract. So our like token standard allows you to have like a Uniswap v2 style contract where that contract emits all the different kinds of LP tokens from its one contract. So you don't need to like deploy a new contract every time. You can just use that one harness, and then the token standard accounts for this identifier design. So basically, like the our ERC20 concept has multiple token colors baked into it, so it's already ready for that. So everything can interoperate, everything can mint these kinds of native assets, and it's a huge superpower because then you don't need to conceptualize managing at the application level, like all the contextualities of those things, right? And smart contracts, when they receive native assets through calls, they put them into their own little balance sheet of all the native assets they're holding. So you can basically manage the amount of native assets you have, the different colors of them internally within a smart contract. Yeah.
Interesting, interesting. Because I would say this is one thing which is a little annoying in Ethereum, if you're doing Solidity, making a function payable or something, or just,
Oh yeah.
dealing with. I know a couple of exploits where in the function itself it has to deal with native ETH and ERC20s, and it just has different different logic, and it just is exploited that way. So actually, this is very interesting. The native
Yeah,
asset system.
let me show you actually this. Let's see if I can get this up here. I wrote up. So basically, I try to test our products a lot, and it's where I get all the friction points, right? And like, it's still eating glass with fuel, so don't expect excellence just yet. It's still a ways to go for us. But I recently just wrote a Uniswap v2 in Sway, sort of like with fuel native assets. It's not using predicates or like that super crazy design where there's no smart contract. This is one smart contract, but this is like what an AMM sort of looks like here. And so you can see when you define your ABI in Sway, nice interface to define the actual ABI. You have depositing assets, which is sort of your entry point for assets and bringing them in, and withdrawals. And then when you're adding and removing liquidity, you specify your asset IDs, and then you can specify where you want to transfer them. And then we have the swap function. So it's very similar to Uniswap v2, right? Add liquidity, remove, swap, etc. Here's my pool structure, my storage structures. So you need the pools, the deposits, the total pools. And what's cool is our SRC20 contract, which is just paying homage to ERC20. It allows you to specify the total supply with a specific asset ID, right? So this is already formatted for multiple native assets per contract, so it's ready for it. If you just have one, then it's just zero, right? But if you have many, then it can work with that, and that's great for NFTs. It's great for this kind of style design, right? It's great for a lot of different kinds of designs. For here, like you can see, this is how we define total supply and total assets, the symbol, everything else, right? And then when you're doing the actual deposit, you can see here that literally I just have this deposit function, and the asset, so the message asset ID, that's the asset ID that's being pushed through the call. So that's how you can actually account for all these different kinds of native assets. You can push them through the call. Here I'm using a bit of storage to manage this. It could all be done in memory, and I can explain that later. But here I use a bit of storage to manage it, and then you can see that literally methods are ready for assets being pushed through immediately, and you don't need to manage these like weird externalities with a proven transfer from per se. You can literally just have these deposited assets, whatever, natively pushed through the calls. So it takes care of the extenuating circumstances around a proven transfer from, where like a proven transfer from, you don't know how things are written. So like you're always building a new concept of like, okay, if I hit this wrong approve or this wrong transfer, like I don't know what I'm expecting. Whereas when you have native assets at the native level, they're just always the same expectations around how the opcodes work, similar to call and pushing ETH into a contract. So basically, like you resolve a lot of extenuating circumstances, and you can still do a proven transfer from style stuff, but just with a lot of less extenuating circumstances. Yeah.
Interesting. Interesting. No, very. The native S system I will definitely look into after our call. I find this super interesting. One last thing you mentioned a couple of times, which is new
Yep.
to me, state dehydration.
Yeah.
Yeah, could you explain that again?
Yeah, so think about it, think about it this way, and this is sort of something we're pitching, and I can send you some stuff that we're releasing soon on this. But the idea is that basically most blockchains just want you to, the only facilities they really give you to manage state and storage are these like local facilities where you store objects, right? So you store them in the node itself, right, over storage opcodes, or you store them, um, you know, yeah, or you store code or whatever. But basically, there hasn't been an evolution in storage, and storage is really problematic because it's on the hot path and it requires I/O, which is the slowest part of processing, typically. So you're pushing it to a drive where you're going to have very slow I/O. And so some blockchains try to solve this by jamming all the active state they think is available or they think that they need to touch in RAM. But that's like a losing battle because now it's like, oh, now it's all got to be in RAM. It's like, holy shit, that's a lot of RAM, right? And so the other solve is to say, okay, well, what do we have physically that we can use to alleviate this I/O burden, right? And what we do is we say, well, instead of having everything be stateful, you bring it over bandwidth. So a basic implementation of this, I think Uniswap did it once with one of their contracts, but instead of storing on chain all the state of the object, having the entire world store it, you just store the hash somewhere. So you store the hash in a state transition, you store the hash of the state somewhere, and then you have people that, hey, you want to state transition this asset or this contract, come in and fill in whatever that hash is, right? And then perform some logic and then recreate the hash and just save that. So it's a simple concept, right? Of just saving these hashes, but don't you think you would rather save the hash and have the world witness the hash than like all these random parameters and information that like should be pruned away, right? That's a better design. That's a more sustainable design. So you can do this at the application level with Ethereum, but of course it's not really the greatest because with Ethereum, you need to use smart contracts for everything, right? And so, unfortunately, smart contracts themselves, just deploying them are super stateful. So, with us, because we have predicates, right, and we have native assets, and you can use assets with predicates and never touch smart contracts, you can basically design the predicate to say, hey, you want to spend, me, the native asset, come fill in the data that makes up my predicate code in my hash and then you'll meet the spending condition. You can spend me. And then with Fuel, we can actually constrain the outputs too. We can constrain the transaction design. And so basically on the spend, you then recalculate a new predicate hash, which would be the state transition itself. And then you save that as the new address. And on chain, that is the most minimal state transition you can make in history, right? That's just the one native asset is moving from one thing to another and both the code and the state has to be rehydrated, right, to state transition. So you can think about it as you bring it over bandwidth, that's the rehydration, right? And then you save it as a hash, and that's the dehydration. And so basically, with this, you can design these sort of very global blockchain systems, but we know for a fact this is as good as it's going to get. It'll never get better than that because that's that's the kind of state transitions you want to have globally, right? Think about a global context. Think about building apps for the entire world. You don't want two people at all ever coming into contact with a piece of state they didn't need to touch. So this is sort of the architecture that we have. And what we want to do is ensure that builders can perform these kinds of things, at the native level. And for us, we just believe our system's really the best at doing this kind of thing. Yeah,
Okay, would it be fair to say dehydration is basically compression and decompression?
exactly. It's just you want to consider what do you want the nodes to really store? Do you want them to store every parameter of your multisig? Like really? Like should they really be bothered by like, the Shafu personal multisig? Now every node on planet Earth has to store like, yeah, he set this to a one and this to a zero and this to a five. It's like, I
Mm.
don't think that's a good idea, right? Because just think everyone on planet Earth, if they had to do that, like I don't know what kinds of computers would we need to use, right, to be able to calculate these things, to be able to do all that. It's too much, right? But if we could store just hashes, that's a lot more. That's a lot better, basically. So
I
yeah.
see, but isn't the everyone saves everything or stores everything also a bit solved by sharding? Isn't that what
Well, think
sharding is
about
trying
it.
to solve?
Yeah, so think about it this way. Sharding does solve things. The issue with sharding is more or less that, and as we've seen, basically, then you're breaking up the potentially the security, right, of each shard into different settings, which is not good. And also, you're breaking up the interoperation of things into different settings, right? And so, all we're saying is just don't store the state here, right? Make everything accessible, make everything the same security in terms of the execution layer you're working with, but ensure that when you're making these state transitions, you rehydrate the state over bandwidth because bandwidth's actually pretty cheap. Like it's prunable, you don't have to store it. It goes over the wire. It can be compressed. It can be, manipulated in a nice way. And as well, builders will store different pieces of the state, right? They'll store different apps and different things that they want, and they'll receive tips for that. So for us, this is a much more sustainable way to build applications because it's not unsafe, right? Everything's still there. You can always rehydrate it. You can always resync all the witness data if you wanted and find it. But basically, I think you're using blockchains more appropriately. And what you really want to track in blockchains is the movement and the settlement of assets, right? You want to know that your assets are stored for you, and someone else wants to know that their assets are stored for them, and that never changes. And like that's like, the movement and settlement of assets is a core piece of what blockchains do. So with the Fuel VM, we try to make that a huge priority in the way that it functions so that global settlement makes more sense with this virtual machine. And that's why you don't want to use WASM or RISC-V or even the EVM for these things. It's not designed for global settlement of people's assets or assets in general. It's just not. The EVM, if anything, is designed for the global settlement of ETH. Like that's what it's really good at, you know? Everything else is up for debate.
That's a big statement, Nick. That's a
Yeah.
big statement.
Well, I mean, I've got the receipts, right? I can show you the EVM spec. So it's very, very good at moving EVM assets around. And then ERC20s are like an appendage to Ethereum and an afterthought in a sense. And when ERC20s, quite frankly, are the basis of Ethereum's value in the first place, right? Like making tokens is a core piece of what blockchains are really about. They're the economic element of a crypto economic system, right? So I think that like we've learned a lot since then. So we can build systems around that, build a better design, right?
Interesting. Maybe. Okay, one question. Aren't you a bit afraid of too much, setting too much focus on the asset stuff? Because maybe for now, 99% of all blockchain stuff is moving assets from one address to another,
Mhm.
but who knows what happens in like 5 years or something.
Yeah, so I think that blockchains are at a more broad and abstract level, right? Global state transitional systems. So they are for transitioning state. Now, the state just so happens to be a lot of assets. So optimizing for that doesn't seem like a bad idea. But I don't think we also not optimize for other things. What we're trying to do is give devs a better way to make better state transitions that are cryptographically executed and verified or approved, right, across the entire planet. And building a better system for that, I think, is inherently a good idea. So it's not like it's only assets. It just so happens that like, most of the state transitions we do are either a non-fungible or fungible state transition of something. So it's like, with a Uniswap pool, that's like an NFT, right? You could say it's like an NFT, right? And then with these other kinds of native assets like coins, those are fungible native assets that move across the system. And it's like if you look at it more practically, like that's really what's going on most of the time. So even when we design things like a Uniswap with no smart contracts, what we do is we graffiti the state of the pools onto an NFT, which seems which seems
Okay,
silly, but that's what it is. And then
I
when you
see.
spend it, you've graffitied the new state, and that's it. And because of the way the Fuel VM works, and because we can introspect like a unique property of the Fuel VM, which I don't think we've gotten into yet enough, but is that in execution you have the whole transaction in memory. So with this, you can do a lot of really cool things. You can create new kinds of conditions over different pieces of the transaction, over outputs, over inputs, over what the script is, over different aspects of how the transaction is constructed. That's super powerful, right? So when scripts, smart contracts, and predicates all have access to the execution, right? Like the actual design of the transaction itself, that like gives you such incredible power to design new kinds of state transitions, because a transaction is sort of the offering of a state transition to a builder, and then all of these different things that happen after are like all the different conditions that get met, or all the different kinds of scripting or stateful things that happen after. And so, again, like providing that facility to the dev is like a superpower, because it just allows you to design really wild forms of execution. And like, instead of designing everything to ram state all the time and change single state elements, etc., like you can actually formulate different conditional state transitions that work in different ways, can be executed ahead of time, can be executed in parallel. And this is really some of our superpower over, I think, some of the other architectures. It's just that like we'll be able to pull off such levels of parallelism because of these instruments that I think it won't make sense to use a lot of other virtual machines. Yeah.
Interesting, very interesting. Yeah, talking about the VM, should we use like the last 15 minutes?
Sure.
And awesome.
Yeah, maybe just to come back to this. So, and just to kind of go more into the VM itself. So, some high level on the VM.
Yeah,
So,
Nick, would be great if you could start sharing your screen again.
oh yeah, sorry. I thought I was.
No
I
worries, no
I
worries.
just didn't do it. But I went to the specs. So okay, so yeah, to talk about the maybe some high level concepts. So the Fuel VM is a register based machine, so it's not stack based. It's register based. It's 64-bit. We have 32-bit instructions, and basically the core concept of the VM itself is that this is a VM for blockchain execution. So that means that it's all deterministic. It's something that can be cryptographically verified. It can be verified in an interactive verification game. And as well, it is metered. So in the optimistic context, it is all gas metered. In the ZK context, you would remove the gas metering. And as well, there are multiple different elements of areas of execution that we've allowed the dev to isolate, such that, as I was describing before, you can get really significant advantages over parallelism. And those are things like predicates. So we have a global memory read and a local write. So the VM has call frames, and basically each call frame in execution can read the entire state of memory. But when you open up a new call frame, it opens up a new sector of memory that only that call frame can write to. So there's a local write restriction, but there's a global read. And that allows you to do some really wild things. Like if you had in one call frame you wrote 30,000 different objects to memory, then when you call, right, the new call frame or a new contract, that contract now can read all 30,000 objects without having to copy the data. It can just read it with pointers. So when you make a call, you just pass the pointers. You don't have to pass all of the data and reserialize it each time. So this is really nice on a contract model where like, you only want to pass pointers. Now, so it turns out in later design, we do copy and reserialize sometimes, but it's only so that you get a new object in memory for the new contract. But in theory, if you wanted to design contracts that referenced all the work that happened in memory before, they can do that without having to, bring it over right to the function. Like if you think about the way that the EVM works, right, you have to copy and then re-encode and then de-encode to make one call, right, between smart contracts. Like you need to ABI encode and then ABI decode just to make a call. Whereas for us, like we can just pass pointers. So it's insanely more efficient if you do it this way. So, and again, as I was describing, there's different contexts of execution, right? There's predicate execution, script execution, smart contract execution. And so basically, there's different forms. And then as well, just to top it off, we tried to define a very clear instruction set. And currently, we don't have any precompiles. It's just ops, it's just opcodes. And we take a lot of inspiration from a lot of different VMs. So we take inspiration from the EVM, take inspiration from Risk, take inspiration from as well CISC architectures because of gas metering and the optimistic context. You basically want to increase the amount of operations you can do on the opcode side because basically if you have many little opcodes, you have to gas meter all those little opcodes, and the gas metering ends up taking just as much execution as doing those operations. So typically we want to actually do it in this other way. And then maybe just to highlight, like, it's a sandbox virtual machine, right? So it's designed to be in its own little sandbox. And the idea again is that most virtual machines out there were really not designed for all these different new ideas that we have around blockchains themselves. So the 2017 architectures that are one form, you have 2014 architectures that are another, and then you have like the Fuel VM, which I would consider the most modern form of a virtual machine design for this. Yeah, maybe just to highlight some other things. So we just allocate a giant chunk of memory per execution, so 64 megabytes. And then as well, we have things like max contract size right now set pretty low, so it's like 100 kilobytes. That could be expanded later, but right now it's pretty low. We have a set of reserve registers that are particularly nice because you have like some basic ones like reserve for 0 and 1, reserve for overflows, right? So we handle safe math and overflowing. The program counter, stack pointers. So we have a stack and heap facility, which is really nice for memory management. And then as well, we have things like an error register, the global gas that's being used, and things like as well the received balance, which again is nice when you have native assets into the virtual machine. You can conceptualize of these things, the return value, right? And then as well like a flags register. And you can have different modes where you can have safe math on or off. And that's the 64-bit safe math. And then as well, like handling overflowing of arithmetic in different ways. So essentially, again, we have these different kinds of execution. Now, one thing to highlight is that if the execution is predicate execution, predicates are stateless, and we design that's by design. So a predicate is a Turing complete but stateless script. And the reason why we want predicates to be stateless is because then you can take them all in parallel, right? You can take all the predicates in a single transaction you can take all the predicates in a block, all the predicates in many, many blocks, and you can just run them all in parallel. And then not only that, if they had cryptographic instructions, you could run them all in parallel, find the cryptographic instructions, then you could send all those to a GPU, then you can have the information come back, and then you can complete all the execution, right? So you can do really crazy kinds of optimization. And so it allows for developers to design these monotonic, isolated forms of execution. And and so that's a superpower, right? When it comes to optimization. So like Solana right now is just doing their GPU version of Firedancer or whatever, and it's like they haven't configured their stuff for monotonic execution like we have. For us to send all the execution of cryptographic execution like signatures to GPUs is really straightforward. So like we've already worked that out. But not just that. Just imagine if you can do now, because we've shown this at least internally, you can build things like Uniswap with just native assets and these monotonic scripts. Well, now you have this whole other set of facility, right, that never existed before, where it's like we're doing the state transitions, we're moving the assets around, we're moving them around like they're all using Uniswap, but there's no smart contracts involved, which is kind of insane. And so anyway, just to touch on some of the meaning while also touching on some of the spec. But as you can see here, we take inspiration from Bitcoin with P2SH. And in terms of execution and verification, again, the ideas here are that because predicates are this different form of execution, we can handle them and verify them in different ways than typical stateful execution. So with an EVM script, you don't really know what EVM code is going to touch in state. Nothing's locked it off. Nothing's really told you what it's going to, be doing. You have no guarantees. So you always have to execute it at brute force, right? And like when you look at like Monad's design or these other things, like it's all brute force work. It's wasted computation, just brute forcing where state's going to change, where things are going to change. Whereas for us, we say like, let's empower the dev to lock off certain aspects of execution so that we know we can always process them deterministically. They're always going to be true or false. They're regardless of state. And that like allows you to build these really powerful concepts with the Fuel VM. But of course, we have script execution, right? And that's where you're basically calling into contracts and you're using smart contracts and you're using state. So script is really stateful. And script sort of has this like revert nature to it, similar to what we have with the EVM. So it can revert. And as well, this is where you're going to have the smart contract execution happening. And then we've locked off deploying of smart contracts as its own concept and its own kind of transaction. Basically because there's a lot of weird externalities when you have constructors for auditing. So like if you have a constructor in the EVM, a lot of contracts will like try to prevent weird calling into their contracts or whatever with constructors, or sorry, with calls, but they don't really think about constructors. And so auditors have this whole section of weird edge cases that are related to constructors because it's like a weird form of execution that people don't think about in the EVM. So we just remove constructors altogether. And just say that deploying smart contracts is like a simple big thing that happens. You can set your state, you can set your immutable variables, whatever. But basically, like that's its own little chunk. Now that is sort of annoying, right? Because it means that you can't do creation of smart contracts within execution. But we actually sort of want that because it just simplifies the whole architecture. And you can end up doing constructor-like behavior by just adding a timer and an owner. So you can just say like, hey, only this owner can call, the constructor function for a certain period of time, and then after that it's constructed. And then basically like construct all your smart contracts, and then once the timer's up, then it all just goes away. And like that sort of time construction is like easy to implement, and kind of covers construction of contracts anyway. So it's generally the case. And then, so this we can get into describing call frames a little bit. So these are just some of the more, the parameterization of setting up new call frames within the VM, like what to expect. And so here again, you have the like the forwarded coins, and that's normally with the EVM just going to be someone forwarded coins from a specific address. Now it's actually like a brilliant design that the EVM has that where like I can force ETH into a call, right? It's like part of making a call is like also financial. It's like I can also force ETH in. But the Fuel VM takes that to the next level and we say, well, you can force any native asset, right, over that call. So you not just have ETH, but you could have your own tokens or USDC or whatever. You can force that through the call. And then that just opens up the design space tremendously because it just reduces a lot of this overhead, right, of ERC20 gobbledygook. And then you have these two parameters here. And that's really where you would fit in your pointers, right? So this is going to be like your memory pointers, the range over memory that you want to send. And so that's sort of like some highlights here, but effectively that's call frames, and then this is just describing memory ownership here, and how that actually works. So hopefully that gives like a sense of the Fuel VM itself. It's actually very simple in terms of the literal VM construction, and then in the instruction set, just to go over that quickly. We have all your standard, arithmetic and logic instructions. We also added native support for big number instructions because, like, let's just face facts. Like, blockchains are using big number instructions. Like, if you use 264 numbers, you typically want the overflow. You want to capture that. You want to be able to manipulate that. And, big numbers are unfortunately now just part of blockchain. So we include those. And then as well, control flow. So lots of different styles of jumps. Again, following more of a CISC architecture of having more variety to do more per opcode because of gas metering. And then as well, memory instructions. So, all the different various kinds of moving the stack around as well, like memory clear, all these different things that the EVM, it took like, I don't know how long to get different opcodes in. Like we just, it's very easy to add them, obviously, if you do a new machine. Then specific contract instructions, right? So opcodes around, stateful things like block hash and the balance of a specific asset at a contract ID. As well, calling contracts, so logging and other things, time stamping, transferring coins. And what's cool is you have these facilities to transfer coins out of the smart contract. So basically transfer the coins out of the smart contract balance out into the transaction to a specific owner or user, or transfer those coins into a smart contract, like another smart contract. So you can move them around, you can move them in and out of smart contracts. We provide some nice cryptographic instructions. We'd actually like to have these done at the application level on the VM itself too, which wouldn't really be that bad, all things considered. But we have them as opcodes anyway, just for ease of use. And that's, like SEPC, P256K1, R1, EDDSA 25519. And KeyCAC and SHA-2 256. We're also thinking of adding or changing this around a little bit. So you just have like a hash opcode, and then at the immediate value, you just flag the mode you want, because we probably want to add more hash functions to this or more signature functions. So we'll look at like compressing that. And then a superpower of the VM, which I love the most, is this dead opcode that does nothing in the base version of the VM eCall. But you get the full register set with that, or all the different registers. And then with this, you can take the Fuel VM, you can extend it and add all kinds of different functionality to whatever you want to do with the Fuel VM. And then you can immediately tool that into Sway. So you can immediately tap into that eCall with a little bit of ASM in Sway. And then now you've got a fully expanded custom virtual machine. So we want to do like a lot of layer 3s with this in the future, where like you write your layer 3, everything we've done with Fuel you get out of the box for free, right? Like all the different tools and infrastructure and data and everything and all this stuff, native assets and all the interoperability. But then you can make that layer 3 and like just customize like all these different functionalities into this one opcode. And then that's your magic opcode that can do whatever you want. And that's where like I think what we think Cosmos and Polkadot got really wrong with blockchain development is really that they gave the dev too many options. And like, I don't want to go and rethink how assets work or how all these different things work, right? And what I want to do is go in and I want to just make one magical opcode that does everything that my app needs, right? So like this whole, construction here just allows you to kind of make those changes. And then we have a bunch of we have a GM opcode, which we felt was extremely necessary. And in the GM opcode, actually, GTF is actually more important. And this actually gives you all the different pieces of the transaction, like where it's located, so that you can basically introspect the transaction nicely in memory without having to parse it. And then, we still got a long ways to go on the spec to flag all the different kinds of failure cases and stuff. It's still not all fully documented. Like we try to describe all the panic cases, but there's still a bunch more. But the idea again is really just that we want an instruction set for blockchain. We want a blockchain virtual machine. We want it designed for this new idea of rollups, the way that we think about builders, the way that we think about blockchains now. And that's really what the Fuel VM is. Yeah.
Amazing, Nick. I could go on for another hour. I have like 8 questions written down, but I think this is a good time to stop here. Maybe we'll do a part two in the future or something. But
Yeah, for sure.
thank you, man, for a great presentation. This was very interesting.
Awesome. Awesome. Well, likewise. It was a lot of fun.
Awesome. Yeah, I'm gonna put the all the links, the spec, your website, the Twitter. I'm gonna put all of them in the description. The GitHub, of course. We didn't have a chance to look at any code today, but maybe part two we're gonna look at some code. Who knows?
Code
Nick,
is surprisingly simpler than the spec, so
that's surprising. That's surprising. But yeah, Nick, listen, thanks again. This was a lot of fun.
awesome. Yeah, thanks. Likewise.
Awesome, guys. See you in the next one. Bye bye.